In this video, we're going to learn how to find the area between curves using integrals. There's a few different ways that they can give you a problem like this. The first one here says find the area between the curves, and they list off 4 different curves. So let me go ahead and see if I can try to graph these. The first one's y equal to x, which is a nice straight line through the origin. Then they give us the line y equals e to the x. Looks something like this. Then they tell us x equal to 1. That's a horizontal line. And then they say x equal to 2, which is another horizontal line. So what ends up happening is these 4 things together create a little shape here. And we're asked to find the area of that. Now, when we're trying to find this area, if it was a nice shape like a rectangle or a triangle, something like that, you could use your formulas from geometry. But it's not. So we are not going to be able to do the shortcuts and get the answer easily. We're going to have to use calculus. What I want to do now is I want to take that shape and kind of recreate just that shape instead of the whole graph. So the top part of the shape is like the y equals e to the x. I'm going to widen this a little bit here. And then we know the bottom is y equal to x, a straight line. So our shape looks something like this. And in order to find the area of the shape, we're going to break it up into a bunch of little pieces here. And each piece, we're going to essentially do a little rectangle. And then we're going to add up all those rectangles using integrals in order to get the final answer. Now, because we want our rectangles to be as thin as possible, we're going to call the width of our rectangle dx. Now, essentially, that's your delta x from back when we learned about how integrals work with Riemann sums. And then you take your limit as that delta x goes to 0. You have infinitely many rectangles, and we're just kind of skipping a lot of that steps and just calling it dx here. So then the real question is going to come is, how tall is this rectangle going to be? Well, when you have these 2 different graphs here, one graph has a y of x and one graph has a y is e to the x. Well, if we just subtract those 2 y values, that's exactly how tall this is going to be. So this is going to be e to the x minus x. And so that means that if I want to find the area here, well, length times width is going to be the e to the x minus x is how tall it is, times the dx is how wide it is. And then we're just going to integrate this from our starting x value of 1 to our final x value of 2. And this is going to give us our area. So if I just do this really quickly here, the integral of e to the x is e to the x. Integral of x is 1/2 x squared. If I plug in 2, e squared minus 2. If I plug in 1, e minus 1/2, that gets e squared minus e minus 3/2, and that will be the area of that weird shape. So this is the process we're going to do. You can kind of simplify talking about it as it's always going to end up being the integral over your interval of top minus bottom dx. It's a good way to remember it. So whatever your top function is minus whatever your bottom function is. Of course, in order to know which is which, you have to know what the picture looks like, which is why I gave little graphing areas in each of these problems. And that's another thing, is you have to know your standard graphs here. You have to be able to graph whatever random function we give you. Now, we do have graphing calculators, and those are wonderful tools, and you're free to use them. But you probably don't want to pull out a graphing calculator for every single one. It might be too much work. So at least some basic graphs you should know. Looking at this next one here, we're looking for the area between the graph of y equal to x squared, which looks something like this, and y equals square root of x, which looks something like that. So it's this little tiny area in between here. Now in the previous problem, we gave you the x equal to 1, x equal to 2, that told you where to stop, where to start and stop on your integral. This one, they don't give you those numbers. However, if you look at the picture, we see that there is a fixed shape right there that we're trying to find. However, they do not tell us what x is. In order to find that out, it's going to be where these graphs intersect each other. And to find where they intersect, we set them equal to each other, and then we're going to solve this. And if you want to solve this equation, we're going to go ahead and square both sides to get rid of the square root. X to the fourth equals x. And then we can go ahead and factor an x out. And you get your two solutions, x is 0 and 1. And so that's what my integral is going to be from. So if they give you in your shape boundaries x equals and x equals 1, x equals 2, then you can get the numbers that way. But if they don't give you those boundaries, you have to find them yourself looking at the picture. So keep that in mind. They might give them to you, they might not give them to you. You have to use your algebra skills to find out what they are. So now if we're going to find this area here, we just said that it's going to go from 0 to 1. We have to know what the top function is, what the bottom function is. Based on my picture, the top function is the square root of x, and the bottom one is your x squared. Then we go ahead and integrate those. Square root of x is x to the 1/2. That's going to go to 2/3 x to the 3/2. Integral of x squared is 1/3 x cubed. And we're going between 0 and 1 here. If I plug in 1, I would have 2/3 minus 1/3. If I plug in 0, I have 0 minus 0. So after all that work, we now know that the area of that shape is 1/3. Now for our third example, I threw a little curveball at you, something that textbooks love to do. They wrote the new equations as x equals y squared minus 4y and x equals 2y minus y squared. Now technically, in like a college algebra class or a pre-calculus class, something like that, you were supposed to cover these. These are conic sections, and when you have a y squared and just an x to the first power, these are going to be either a left parabola or a right parabola. And in fact, you're going to get one of each here. You're going to get something that's a right parabola, and then something else is a left parabola. But you'd have to do a lot of work to try to get those graphs accurately. Also, if you want to try to use your graphing calculator, it's not going to help you right now. And the reason why it's not going to help you is because in your calculator, when you go to graph, it always says y equals. And your graphing calculator only knows how to handle y equals for this. They don't know how to handle x equals. And so your graphing calculator is no good. There is going to be a better way, and I'm going to show you very quickly how to do that. But before I show you the better way of doing this problem, I want to point something out. What we've seen in the first two examples was when we integrate, we do top minus bottom. Well, take a look at our shape down here, and let's say I look right here. Well, at this point in time, I have the blue parabola on the top and the blue parabola on the bottom. On the other hand, I might get to a point, and this is not perfect, I know because my picture's not perfect, but you could have a point, depending on exactly how the parabolas are, where you have the red graph on top and the blue on the bottom, or you could have one where the red's on top and the red's on bottom. So the thing is that any of these is a possibility, and even if we were to draw the graphs more accurately, it's going to change which graph is on top and which one's on the bottom. As a result, you cannot just do your integral to get the answer. You're going to have to break it up into multiple integrals, changing which one is on top and which one's on the bottom. And it's a big hassle. The way that most textbooks would have you do this is instead of trying to do that, they would say, okay, don't draw your lines like this. Instead, draw your lines horizontally. Because if you draw your lines horizontally, you always have the red graph on the right and the blue graph on the left. But if you do it horizontally, your width of these shapes is not dx anymore, it's dy. So it's perfectly valid to do an integral where it's, instead of top minus bottom, it's right minus left as long as you're doing your integral with dy instead of dx. That is the way that most textbooks would show you how to solve this problem. And it works, it gives you the answer here. But in my experience, students have a lot of trouble with that, suddenly shifting to doing dy and trying to understand that. And I have what I think is a better way. So I'm going to get rid of this here, and I'm going to show you the way I always approach this problem. Now, you guys have gone through a lot of math in your life, and when they first taught you about coordinate systems, they always taught you got the x-axis and the y-axis, and you do all your graphs and so on like that. But the thing is, the reason why x is in the horizontal and y is in the vertical is just because someone decided that's how it should be a long time ago. There isn't anything inherently correct about x being horizontal and y being vertical. It's just the standard of what we use. Math would work out perfectly fine if you had had y on the horizontal and x on the vertical. Math would still be just fine on that. You just have to change how you viewed everything. And so the trick that I show my students for this is take this set of equations and switch around what your x's and y's are. So everywhere you see an x, you're going to write a y. And everywhere you see a y, you're going to write an x. So instead of x is y squared minus 4y, I write y is x squared minus 4x. Similarly, instead of x is 2y minus y squared, I write y is 2x minus x squared. And just by that simple change, I now have two equations that are more familiar to us, that we're more used to handling. Also have two equations that you can put in your calculator no problem. And the thing is, as long as you switch x and y everywhere, it's going to be the exact same problem. You're still going to get the same answer, even if it looks different. And it essentially just corresponds to turning your head on its side and switching how you view x and y. And again, I'm telling you right now, it's mathematically valid to do this, and it's going to make our life easier. Now, both of these are parabolas, right? We got the x squared there. We can use our vertex formula. X is negative b over 2a. Now, I'll skip a little bit of the work in doing these graphs, but you can take your time or use your calculator for this. So for the first one, the vertex is going to be x is 2, and if you plug it in, you're going to get 4 minus 8 is negative 4, so it's going to be down here somewhere. So this is your first parabola. And then if we look at the second parabola, we're going to have negative 2 over negative 2. X is 1 for the vertex. If you plug in 1, you get 1 there. And so this right here is your second parabola. And here's our area. Now we need to find these intersection points, but you can do that by just solving them equal to each other. So if I take x squared minus 4x is 2x minus x squared, that gets 2x squared is 6x. Go ahead and factor out 2x here. And we get the intersection points x is 0 and 3. We don't really care about the y values here. So that means my area for my integral is going to go from 0 to 3. The top function is the purple one, which is 2x minus x squared. The bottom is the x squared minus 4x dx over here. Running out of room, sorry. And then this is going to work out to be a negative 2x squared and then plus 6x dx. You can integrate each of those terms here. Negative 2/3 x cubed plus 3x squared from 0 to 3. Plug in 3 here. That's negative 18 plus 27. Plug in 0. And our final answer is 9. And again, in my personal opinion, that's a lot easier than trying to do everything with y's and not get confused by that. So I would recommend every time you're given a problem like this where it's in terms of y, You can deal with it that way, or you can just swap everything and make it more similar to the other questions you're dealing with.